I agree 100%. Because if we compare this to a uniform application, yields are not going to be affected. But what is being improved is our margin of profits, as we have a more economical system to spray herbicide. Okay, so having said that, let me bring you to some data from Arizona to highlight what about that distribution of weeds that we have locally. So I'm convinced that everybody in this meeting knows that there are a lot of weeds and they're distributed all over the place. But how random is this, and how much of a variation there is? This map can help us understand that part. So this is a map from a field in Yuma, Arizona last week. And what we did is we scanned the field with a spectral sensor. And you see here on the scale that all the dots that you see in that map that are pink, red, and yellow, those are really referring to the spectral response when there are only plants in the field of view of the sensor. Everything else is the crop and weeds that are present in the field of view of the sensor. So you can see that a couple of observations. One is how random this is, but the second is it's about half. Half of the field doesn't have weeds. Half of the field does have weeds. So it makes sense from only that very simple analysis. It makes sense to have a technology that can recognize where there's a weed and spray it. Okay, right there you will have a savings of 100% of your 50% of your chemical use. Okay, so this is just to introduce us to a more local context. I want to explain the principle of operation, just in case somebody is new to these type of systems, which are new. They started in the early 2000s. What I have here on the left is an image of a system called Weed Seeker. The first part is that this is an active sensor. It is emitting light. And that light is bouncing back from the plant because a portion of that light is being absorbed. So the sensor looks at how much light is shining through and how much is returning. And that difference is how they can compute that there is indeed a weed. That signal will be very different if 1 and 2 are hitting the ground. Okay, 1 will be equal, but 2 will be almost 0. Just to make a point there. Number 4, well, there's a processing step in number 3. The number 4 is the control system that I mentioned earlier. That once a weed has been detected, then the system is enabled to spray. Okay, so in a very simplistic way, that is the principle of operation. I like the picture on the right, how clear they put this weed being sprayed. Okay, so back again to Arizona. In the early 2000s, there was a significant amount of work done on this, using this technology on a variety of cotton farming systems. Like in this picture, there is a conservation tillage type of system, and it was used there. It was also used in more conventional settings. So one of the problems that was found back then with this is the earliest technology, the earliest version of this technology, is the effect of the soil background. It was a manual adjustment of sensitivity. So with this system, if you put it too sensitive, it was just going to be spraying all the time. Makes no difference to a uniform. But if you wanted to reduce the sensitivity, it was missing many plants frequently. So anyway, that's the work that was done. It's well documented, and it's been very useful. But now the picture on the right is showing you what are the newer systems that are the new versions of this technology. And this particular image is from a system called With IT. I believe it's manufactured in Australia. So we've been doing some testing this season, 2020, although we were a little late in the season. So everything that I will present today, it's really preliminary work. Next year we'll have more solid replicated trials. So, but that is kind of a picture of the old and 20 years later. Now, as far as options, the picture on the left is that With IT system. The picture on the right is a Trimble WeedSeeker Generation 2. So both of those systems are commercially available now. I think WeedSeeker is only its second year in the market. Now, With IT is a standalone system. So there is a controller that is connected in the cab of the sprayer, tractor, whatever it is. The system on the right, Trimble, that interfaces with any of your Trimble displays, like a FMX or something. So the advantage in that sense is that Trimble can then map your fields and log information the way you do it for many of other Trimble enabled operations. So this is an add-in to Trimble's functionality. So very well, it's known that there are improvements in sensitivity. These systems now use more processing power, and they are able to make better distinction of in weed detection than the previous versions. And nowadays we have rate control much improved, and only one, if I were to mention only one case, that is pulse width modulation. So these systems enable pulse width modulation very easy, and it's great for speed compensation and variable rate as well. So our work, the way we see it in 2020, is that we're focusing on generating information to see how we can adapt these systems. Even from the pictures that you can see on top, you see that this is not cotton. This is not even a row crop of some kind. So I'm going to go back to the previous image. This is our cotton. And this technology needs to be adapted to our systems in cotton to be useful. So on both cases, you see that there are hoods, spray hoods. So we think that there are improvements that we can make on hood configuration, the width, and the size, and position too, and along with many other operational parameters. So that's our focus. I'm going to play a small video. I had two reasons to put this video here. The first and most important one is that Peter Ellsworth is going to see how much wadflies there are in this field. Second, less important, is that you see how this system operates, and it's played at half of the speed. Here we go. So for the entomologists, you see the wheels turning, all these small white spots are whiteflies. But for the engineers in the room, you see how the system is spraying. There's a dye, there's a chemical dye in the mixture, and there are many misses. There are many that are weeds that are sprayed. This was intentional. Let me tell you, I'm not saying anything that is wrong with the system. It's just we test different parameters at a time, so we had to have that resolution. So this was intentional, but the way you see that spray happening is how it works. Okay, so again, I'm saying this as a set of preliminary results. We want to share it with you to give you a sense of the work that we're doing. But just bear in mind, it's still preliminary. So these results are coming from the Safford Ag Center. Randy Norton conducted this test. The image, the graph on the left, it's only for small weeds. What's the control efficacy of this system? Varying the sensitivity levels from 1 to 5. Okay, and what Randy defined as small weeds is anything smaller than a quarter coin. So you see that there is overall, these are overall averages. There's some variation, especially in sensitivity 3, but in the end, the efficacy was between 80 and 90%. Okay. By the way, I want to be clear on this. We are aiming 100% efficacy, or the closest that we can get there. Okay. When you compare to the image on the right, that's all weeds, smaller and bigger. These are the results, and there are similar trends to some extent, but when you see overall weeds, there are it was lower. Okay, so we're still in the process of understanding what's driving these factors and generate a technological package that can be useful for our cotton in Arizona. So that's all I have for this sensor control spot spraying. But I want to use 2-3 minutes to talk about something that I think it deserves some level of attention and understanding as well, because we see everywhere now in news reports about smart farming, digital agriculture, and things of that nature. In our context, I think I have a view that I want to share with you, okay? And I'm going to do this historically. So back in the 50s, early 60s, there's this series of Closer Than We Think. So Mr. Rodebaugh made a number of drawings and indicating, suggesting, even by the title, suggesting that this is something that we're going to see in the future, okay, near future. And you see the way he conceived farm automation is with autonomous vehicles. Now we're seeing some of those, okay? So, and communications and control, all those kinds of aspects are kind of embedded in that futuristic view, okay? So it's interesting to just to see 50 years later what we see today. Now, I happen to value this type of rendering and ideas that were floating back then, but I tend to analyze this digital inputs with a slightly different take. So let me take you to historically, one of the earliest papers that talked about the increased use of digital inputs in agriculture was Professor Bill Chancellor out of University of California, Davis. So he wrote this paper in 1981, and all the calculations that he made were based on a computer like the one you see in this screen. So 1980s, you can only imagine how much more processing power we have now with our computers 40 years later. I mean, it's a logarithmic change, okay? But his main premises was the following, and this is what digital agriculture really means in our context in production agriculture. And that is increase the information processing capacity of individuals engaged in agriculture. And by the way, I forgot, it's processing and handling information, okay? So let's see how this, again, talking about kind of predictions towards the future and things like that. He presented this table. We say, if there is computer power to control certain operations, the energy savings will be great, okay? And the efficiency will be much higher as well. Tractor transmission control, that's what we call now infinite variable transmission, IVT. Traction wheel slip control, now we have central inflation systems on big machines. Irrigation water application, Well, there's a lot of work now in variable rate irrigation, fertilizer placement. Now we have variable rate fertility management. Control of tobacco, I don't know what to say on that one, but cotton gene management is clearly much more automated and sensor control. So my point in these last two slides is to show you this is really the basis of our work. We're engineers, we're working on this as we see how this flow of information can benefit us in our production systems. Okay, we don't tend to go for the latest and the more sexy technology that is out there. We tend to analyze it how it's going to help us solve our needs. Okay, so I want to finish there, recognizing the support from Cotton Incorporated and the Arizona Cotton Growers Association, their financial support, but more than anything is the institutional support from Cooperative Extension. So thank you. I didn't keep track of time, so maybe I'm over my time, Hyman.